All right, so now that we have a good visual, a good understanding of what was happening, how do we find the actual surface integral? Well, we have to it said use Riemann sum, so we're doing approximations based upon those dots. So what we need to do is we need to find the top and the bottom areas. So if we talk about the bottom area, well, it's just a disk. I mean, it is a cylinder. It's just a circle on the bottom. It's a disk. And the area of a disk, of course, is pi r squared. And the radius of that disk, based upon the fact that this is the shape of the cylinder right here, the radius is 1. So the bottom area is pi times 1 squared, which is just pi. And the top area is going to be exactly the same thing. It's also a pi r squared. Doesn't change the fact that r is 1. So we also get pi. But now what we have to do is we have to multiply that in order to get our surface integral. We have to multiply that by its value, its density, it's whatever that they've given us here. So the surface integral part is going to be f of xyz, which they gave to us, times the area of each piece. Well, f of xyz in each piece is 4. The area is pi, 4 pi. So what we're going to get out of that is 4 pi and 4 pi, so we get 8 pi out of the top and the bottom. Now what we have to do is we have to break up the lateral surface area of the cylinder. Well, if you took a cylinder and you opened it up so that it's flat, the lateral side of a cylinder is nothing more than a rectangle. So it's going to look something like this. If you were to open it up. And it says that we're supposed to split this thing into 4 equal sections. So let's see. 4 equal sections. There we go. And what we've got is we've got some kind of representation, some kind of a dot for each one of these sections. So, you know, if I'm looking at the x-axis pieces, the positive and negative 1, 0, 0, then what you're talking about is a little dot right here, and then another little dot on the other side right there. That might be where, if we open this thing up, that's where 1, 0, 0 and negative 1, 0, 0 were. And then if we were to look at the y piece, that's going to be the green ones here. Those were a little bit bigger, and that would be at 0, 1, 0 and 0, negative 1, 0. Well, we need to find the area of the entire outside port of the cylinder. Well, the area of a cylinder, when you open it up like that, well, the top part here is the circumference, which is 2 pi r. That's just the top ring. And then the height of this thing is 2, because it goes from negative 1 to positive 1. And that distance there is 2. So the height is 2. So the total area of this is 4 pi r. But we know that the area, the radius is 1. So we get an area of 4 pi times 1, or 4 pi. So if we're going to split this into 4 equal sections, then that means each one of these pieces is pi. Because the whole area is 4 pi, and these have to be equal sections. Well, okay. So I know that the red dot represented, actually I have to go back up and look at that. The red dot, which was the x one, it represents 2. So each one of these pieces with the red dot has to get multiplied by 2. So each one of these is going to get multiplied times 2 times 2. And then the ones with the green dot, I believe, was being multiplied by 3. So each one of these gets multiplied by 3, because that's the density, or again, whatever they've given us there. So ultimately what we get from this whole thing is we get, let's see, that'd be 2 pi out of the first one, 3 pi out of the next one, 2 pi out of the third one, and 3 pi out of the last one. And we have to add all those things together. Adding those together gives us 10 pi plus the 8 pi that we had from the beginning. So the whole thing is 18 pi. Okay, and that was because they wanted us to use Riemann sums as opposed to actual functions to be able to figure this thing out. The next examples we'll be doing will be the actual process that it takes to get from some kind of a surface to its surface integral. Okay, our second example says it wants us to find the double integral over S of z ds. So it's definitely a surface integral because it's telling us over S, and of course ds means over the surface. So if S is the surface, x equals y plus 2z squared, and it's telling us that y is bounded from 0 to 1 and z is bounded from 0 to 1 as well. So in order for us to do this, okay, we need to find f of x, y, z, because that's what this thing is. It's going to be some kind of a function of 3 variables, and reduce it down into 2 variables. Well, looking at the function, the surface that they gave us here, this surface right here it's not spherical. It's not a sphere. It's not a cone. It's not cylindrical. And because it's really not any one of those 3 specific things, you probably don't want to put this thing into spherical or cylindrical coordinates, so we're probably just going to go with the trivial parameterization here. And remember that the idea for the trivial parameterization was you're going to let 2 of the variables just be themselves, and then the third variable will be a function of the other 2. So in this case, it looks like x is a function of y and z, the way we have this thing written. So we're going to let y equal y. We're going to let z equal z. And then we'll let x equal a function of y and z, which is y plus 2z squared. So now all of these things are in terms of just y's and z's. So that tells me that my r, in this case, r of y and z, is going to be, well, the x part goes first, so y plus 2z squared, y is y, z is z. Okay, and we needed to do that because we needed to parameterize this thing. And then we're going to be able to reduce the double integral over a surface to the double integral over a domain. But remember, the domain is going to be what it takes for y and z to create the surface. All right, so in order to do that, we do know that we are going to have, let's go ahead and I'm going to put this down here. We're going to have the double integral over S of some function of x, y, and z, ds. We're going to reduce that to some double integral over a domain. And remember, the domain is our function of r of yz multiplied by the cross product, because this is our ds part, r sub y cross r sub z dA. So then we'll just be able to take the area of the y and z part, and they've given us bounds for y and z right here, which is wonderful. That is going to make it really easy to do. So what we need is that cross product. So our cross product, first of all, we need r sub y. R sub y is going to be, let's see, the partial with respect to y is going to be 1, 1, 0. Yeah, that looks right. And then we need the partial with respect to z. The partial with respect to z is going to be, what is that, 4z, 0, 1. And then we need to cross those 2 things, so we'll need ry crossed with rz. So if we do the cross product, remember, I'm not going to write the ij and k across the top, but the way it's set up right now just like it would be a determinant. So if I eliminate the I row and column, that's just going to give us a 1. If we eliminate the j row and column, that's going to give us 1 minus 4z. But remember, that has to be, is that right? 1, no, I'm sorry, it's 1 minus 0. It's even better. So that's just negative 1. Because it would be 1, but you have to change the sign. And then if we eliminate the j row and column, that's 0 minus 4z. So it's just minus 4z. And then what we're going to need is the magnitude of that. So we need the magnitude of ry cross rz. which is the square root of each one of the pieces squared. So we're going to get the square root of 1 squared is 1, negative 1 squared is also 1, 4z squared is, or negative 4z squared is going to be plus 16z squared. So that's going to simplify to square root of, doesn't really simplify much more than 2 plus 16z squared, I don't think. Yeah, I think that's probably as good as we're going to get right there. Okay, so we've done what we needed to do. We've parameterized it. Now let's go ahead and plug our information in. So we're going to have the double integral of our function of y and z. Well, our function of y and z is just z because that is a function of y and z. It's just z. So z on the outside times our magnitude of the cross product, which is the square root of 2 plus 16z squared dA. But dA is with the terms of y and z, so it's going to be dy dz. Technically, we could do dz dy, but in this case, it makes much more sense to do dy dz because we are going to have to take the derivative of this thing. Actually, it doesn't matter. These are constant bounds. We're going to be able to split it. Never mind. Order won't matter here. You could do dy dz. You could do dz dy. I was thinking that we had to get an extra variable on the outside, but we don't in this case, so we're okay. So from here, we can split this. So we're going to have the integral from 0 to 1 of just dy times the integral from 0 to 1 of z square root of 2 plus 16z squared dz. Integral from 0 to 1 of dy is going to be pretty easy. That's just 1. The next one, we're going to have to do a u substitution. So in this case, u is going to equal 2 plus 16z squared, making du 32z dz. So dz is going to be, was that du over 32z. I'm going to go ahead and change the bounds. So our bounds are now going to go from, let's see, plugging in 0, we get 2. Plugging in a 1, we get 18. We get z square root of u, which is u to the 1/2 power, times the new dz, which is du over 32z. So the z's are going to cancel. That's going to leave me with a 1 over 32 that I can bring out to the front. So let's go ahead and do that. Times 1 is still just 1 over 32. Integral from 2 to 18 of u to the 1/2 du. So let's take the antiderivative. That'll become u to the 3/2. Multiplying that by 2/3 out in front from 2 to 18. The 1/32 over 2/3 is going to simplify to 1 over, let's see, what's 16 times 3? 48? Yeah, so 1 over 48 times 18 to the 3/2 minus 2 to the 3/2. And technically that is your answer. I'm going to go ahead and simplify this thing just because I kind of have a need to. Just to me, it doesn't look simplified enough. Remember that something to the 3/2 is that thing times its root, its square root. So we're going to have 1 over 48 times 18 root 18 minus 2 root 2. But 18 can be simplified. Square root of 18 can be simplified to 3 square root of 2. So that's 1 over 48. Let's see, 3 square root of 2. So 3 times 18 is 54. Yeah, 54 square root of 2 minus 2 square root of 2. 54 square root of 2 minus 2 square root of 2 is 52 of them. So I get 52 root 2 over 48. 52 over 48 simplifies, what goes into both of those? 4, I think. 4, so that'd be 13 root 2 over 14. Okay, that's the most simplified form. You could have stopped right here, and that is perfectly acceptable. That is the right answer.